let's go to the ARM web page and directly look at the summary of the individual registers. Okay, so this is the web page from ARM which corresponds to a summary of the entire set of registers that are present for the UART peripheral. On the left hand side you can see various things, the entire data sheet corresponding to the UART. It gives you the technical reference manual, it gives you the functional overview, which we are not really getting into, but as you can see over here, the functional overview is, it tells you certain things like, for example, what does the UART contain? It contains a programmable baud rate generator, it contains, and these are the different kinds of maximum baud rates that it can handle, right, and various such pieces of information that as a user you would be interested in knowing, right. It also has the functional description which talks about the interface that you have with the different parts of the system, right. But as far as we are concerned, the important point is the programmer's model, and in particular the summary of registers. Okay. So, I am going to sort of look at the summary of registers in a little bit more detail over here. So, there are a few things that I want to focus on as far as this table is concerned. The first is, look at how the register layout is specified, right. It typically has an offset, a name associated with the register, a type which you will see is things like RW, RO and so on, right. What is the value under reset conditions, what is the width of that register, and a brief description, right. And this description is intentionally very brief, it sort of is just a one line description. For a more detailed functional description, you can of course click on these links, and each register has a more detailed description. Now, if you had a data sheet as a PDF file, you would have exactly the same thing, but without the, instead of the clickable links, you would just have like pages and pages which sort of describe the entire thing to you. Now, let us try and understand this. The first things first, right, we can look at this part and say, okay, there is something called an offset, and this offset, as you can see, is a hexadecimal number, and because it has 3 hexadecimal digits after the X sign, it means that it is a 12-bit value. Okay. Now, this is interesting. Basically what it tells you is that the hardware that you have created has a 12-bit address space, right. The address block corresponding to the UART occupies 12 bits. What does that mean? It means that I could, for example, say that the UART addresses start from address number 0, and from there they will go on until address number 4095, because 2 to the power of 12 is 4096, right. Now, instead, if you said that it started from, let us say, the address number 1 meg, right, which is 1048576, from there you would say the first, the 0th location, the address corresponding to this register which has the name UART DR, right, will be at address number 1048576. The address corresponding to the UART RSR would be 1048576 plus 4. The UART FR would be 1048576 plus 18 hex, which is 24 decimal, right, and so on. As you can see, because it has 12 bits, you go all the way up to 4092 as the last address, because each address over here is considered as a 4-byte location, or rather we increment the addresses only in 4 bytes, but the addresses themselves refer to individual bytes, right. So, I have a 4 kilobyte address space associated with the UART, right. So, you might be wondering, why do I need 4000 locations to store the registers corresponding to a UART, and the answer is you do not, right. But it does not matter, because typically the address space that is provided for your processor, nowadays modern processors would be at least a 32-bit address space, and many of the newer ones might even have an address space bigger than that, or rather an address bus which is wider than 32 bits. Now, 32 bits is quite a lot of addresses, right, it is basically around 4 billion addresses, and if you extend it, let us say, to 40 bits, you would find that that goes up by another factor of 2 power 8. So, in other words, it is unlikely that you are really running short of addresses, which means that it is often simpler to take a large chunk of addresses, maybe an entire 12-bit address space, 4096 locations, and associate it with a peripheral, even if the peripheral only has, let us say, 2 or 3 registers that you are concerned about. And this is quite common, right. In this case, of course, it is not 2 or 3, you will find that this UART actually has like tens of registers, but it's nowhere near 4000, right. So let's look at a few of these registers. As you can see, at offset number 0, we have a register called UART DR. It says over here that it is RW, which means that it is a read and write register. You can either read from the register or you can write to it. It also says that under reset conditions, it's given as blank, right. So basically the dashes indicate a don't care state. In other words, immediately after reset, if you read the value in the UART DR register, there is no guarantee as to what value you will see. It also says that it has a width of either 12 or 8, which basically means that this offset 0x000 actually corresponds to a 32-bit register. Why 32-bit? Because that is the standard data register size in ARM, and therefore it is assumed that each of the registers is a 32-bit register. But what this says is that only 12 of those bits are actually used, at least in the read mode, and another 8 of them, or rather not another 8, but only 8 of them are used for writing. In other words, if you try writing into this register, only the bottom 8 bits will be used. If you try reading from the register, 12 bits contain some useful information. Now, to understand this, we will actually have to go into the details of what the data register looks like, right. And we can do that. We can just click on that link, the data register UART DR. It tells you, for example, there are words to be transmitted, and if data is written to this location, it is pushed onto the transmit FIFO, and if for received words, if the FIFOs are enabled, the data byte as well as a 4-bit status, right, break, frame, parity and overrun is pushed onto the 12-bit wide receive FIFO. So this is why it showed a width of 12/8. If you are reading, in addition to the 8 bits that you get of data, you will also find another 4 bits that are coming back, or rather 8 bits of data, you will find 4 bits corresponding to the status flags. Now, in this case, what they have done is they have only given the information corresponding to the 16 bits of what is there in the data when you get it back, right. It also says that bit number 15 to 12 are what are called reserved bits. Remember what I said about reserved and unused bits? Just like we have reserved and unused for the address space, in the same way we also have reserved and unused in the context of individual bits inside a register. When it says that bits 15 to 12 are reserved, you need to infer 2 things from it. One is, if you do write something to bits 15 to 12 of address offset number 0, right, in the ARM UART peripheral, it basically means that there is no guarantee on how the system will behave. You are not supposed to do it, you should not be writing into those bits. Similarly, if you do read from them, you may find that the returned bits have the value 0, but it does not guarantee that. It just basically says they are reserved. ARM may later choose to add some functionality there, so you should not rely on the fact that these are going to be 0 when you read them back. Okay, so out of the 16 bits, in other words, we have basically said that 4 of these bits 15 to 12 are not required, or rather are reserved, and therefore you cannot rely on their value. Bit number 11 is what is called an overrun error. It is set to 1 if the data is received. I am not going to go into the details of each and every one of these bits, just very quickly talk about them. Bit number 10 corresponds to a break error, bit number 9 is a parity error, and bit 8 is a framing error. In other words, each of these indicates some kind of problem that happened when the data was being received. And bit 7 to 0 would be the actual data that was received. This is after removing the start bit, removing any parity bits, whatever are the remaining 8 bits of data that came back would be what you receive as the data bits, right. And clearly, if there was some error that occurred, then the data should not be relied upon, and all of this is of course in read mode. The interesting thing is you could also write, in which case you are not really supposed to write into any of these bit number 11 to 8. You should be writing only into bits 7 to 0, which basically corresponds to the transmit data that you want to send. So, all of this is a detailed description of one particular register, the UART DR, that is present inside the ARM processor.